Okay, so the exams I'll get back next week, and let's put off talking about the test until then, and then I can go through all of it or as much of it as you want. Remember, if it felt like it went badly, remember that one exam doesn't even have to count for your grade. So you can think of, because the fifth exam can replace the lower of your first four. So if it didn't go well, think of it as like, okay, you get a mulligan, that's all right. But, you might want to come talk to me or at least spend some time thinking for yourself about, what didn't go right in your preparation. Were you thinking about what I was going to ask wrong or so please come talk to me in office hours or send me an email or something if you want me to help you think through that. I'd be happy to. But like I said, the test will be back next week, and then we can go over scores and whatever after that. So now we're going back to vectors. Yeah. Okay, so back to, well, really the overall topic is 2D kinematics of particles. And before we can do problems in 2D kinematics of particles, we have to learn how to do vector calculations. So we talked about the intuitive physical meaning of adding vectors and multiplying vectors by numbers. But that's not the way we're going to do calculations. So now I'm going to talk about vector components, expressing vectors in components, and using those in calculations. So in classes, you usually won't do graphical vector calculations. Instead, you'll define a coordinate system, CS, coordinate system, and express vectors as components. And so to do that, if you have a vector like, let's say this, okay, that's just an arbitrary vector. First, you have to know what your coordinate system is. In math classes, you really never change the orientation of a coordinate system, but and that's because there's really no mathematical meaning to changing a coordinate system. But sometimes you will have to deal with different orientations of coordinate systems in physics and engineering because the coordinate system represents a relationship with the physical world, okay? So in math, all coordinate systems have the x-axis that way, the y-axis that way, because mathematically you can treat everything that way. But in the physical world, if you're rolling something up a hill, you might want a coordinate system where the x-axis points up the incline of the hill and the y-axis is perpendicular. Later, we'll talk about why you might do that. So all that is just saying, first thing you need to do is figure out what the coordinate system is. So, but let's say we're using this one for now. There's the negative x-axis. There's the negative y-axis. Then you put the tail of the vector at the origin. So move it over so the tail is at the origin. And then we can break this vector up into one component that's parallel to the x-axis and one component that's parallel to the y-axis. So in this case, you can represent this vector as the sum of two different vectors, one parallel to the x-axis like that, and one parallel to the y-axis like that. These are always perpendicular. This vector is the x component. And this is the y component. And so now we're going to break up the vector into the sum of a vector parallel to the x-axis and a vector parallel to the y-axis. And if the x component is in the direction of the positive x-axis, then you say that that component is, you give it a positive number that's equal to its length. And if it's in the direction of the negative x-axis, it's a negative number with its magnitude equal to the length. And same with this, with the y component. If it's in the direction of positive y, it's a positive number. Negative y, it's a negative number. And so the components of the vector are the coordinates of the vector's head. Okay, so in this case, if you think of it as the sum of two different vectors, you have to go in the negative x direction and then in the negative y direction. Okay, and if you wrote that point as coordinates, you would have a negative x coordinate and a negative y coordinate. Okay, and we'll represent vectors this way. As a ordered pair. We're going to do it as a column vector, as a column matrix with, so this will be the x component on top and the y component on the bottom. And the x component is the x coordinate of the vector's head, and the y component is the y coordinate of the vector's head. People represent vectors in a lot of different ways. I'm going to use this form mostly. I'll talk about the other common one in physics in a second. But this is useful for a lot of calculations you'll end up doing with vectors later, and that's why I'm going to put it in this form. One way that always works always works for calculating vector components. Is to first, like we did before, put the vector's tail at the origin. Then figure out the counterclockwise angle theta from the coordinate system's positive x-axis to the vector coordinate system. And CCW is counterclockwise. And then the components of the vector, and any vector we're going to denote with a arrow over the top, that's the symbol saying a variable is a vector, is equal to L times the cosine of that angle theta, L times the sine of that angle theta, where L is the vector length. Okay, so for example, let's say that we have a vector makes an angle of 20 degrees with the vertical like this. And let's say it has a magnitude of 10. So that's the length. What are the vector components in, and we're going to do 3 separate coordinate systems. First, in the coordinate system orientation that we're most used to, second, in a coordinate system with the x-axis straight down, and the y-axis then has to be to the right. And third, with the x-axis this way and the y-axis this way. And this angle is 20 degrees from vertical. Okay, so even though it's going to be the same vector in all 3 of these cases, the vector doesn't change. We're going to have different components for each of these coordinate systems. So first, for A, so I'm going to draw the coordinate system. I'm going to draw the vector with its tail at the origin. So here's vector. Okay, and we know that this angle is 20 degrees. And we know that the length of that vector is 10. So what's the counterclockwise angle to go from the positive x-axis of this coordinate system to the vector? Yeah, you could do it. Well, actually, you can do it infinitely many ways, but there's probably only two ways that really anybody would choose. One is to go around counterclockwise and call it a positive angle. So that'd be 90, 180, 270 plus 20. So 290 degrees. Or the other is to go clockwise and call it a negative angle. And then theta is equal to clockwise 90 and then backtrack 20. So negative 70. Yep. Yeah, anytime you go counterclockwise, it's positive. Anytime you go clockwise, it's negative. So you can think of it as like a series of steps. So clockwise, negative 90, negative 90 to there. And now counterclockwise, so add 20 to that, and you get negative 70. And so the components of that vector are the magnitude of the vector, 10, times the cosine of either one of these. You get the same thing either way. And so plug that into your calculator and you get 3.42, negative 9.40. Or, so that always works. You can always do that. Or you can just do the trigonometry yourself in your head. Use SOHCAHTOA. If the signs have to be the signs of the coordinates of the head of the vector. So we know that here we have to have a positive x component and a negative y component. And so you can use this triangle SOHCAHTOA and come up with those components. That works fine too. But you can always just measure that counterclockwise angle and it'll give it to you. Any questions about that? Okay, so now let's go to the second coordinate system. It's the same vector, but the coordinate system is different. So now the x-axis goes down, the y-axis goes to the right. And I'll extend the negative axes. Since it's the same vector, changing the coordinate system doesn't have any effect on that physical vector. So it still points like that. But now the x-axis is in a different place. So what's the counterclockwise angle from the positive x-axis to that vector? 20. Yep. So the vector components are 10 times the cosine of 20, 10 times the sine of 20, and we get 9.40, 3.42. Yeah, so the way that I'm explaining it, you start at the positive x-axis, wherever that is, and then you go counterclockwise until you hit the vector. Always, if you want to call it positive, go counterclockwise. If you go clockwise, call it negative. So you could also, probably no one would do this, but you could also go clockwise 340 degrees. Plug that into your calculator. Be sure your calculator's in degrees and degree problems, and it'll give you the same answer.
If it's like the other way around, like y x, then you have to. Then it's basically typically be 290 because you're from the x-axis.
Yeah, just wherever the x is, start at the positive x-axis. Okay. Don't start at the negative, and go till you hit the vector. By the way, what are the units of these vectors? That's right. A vector is a mathematical thing, just like a number is a mathematical thing. Like asking the units are of a number, depends what that number represents. So we'll, and so if that number represents a force, then we haven't talked about that. If the number represents an acceleration, then the units are meters per second squared, and it's going to be the same with vectors. All of the things that were directional quantities for motion along a line, position, displacement, velocity, and acceleration, are going to be vector quantities in 2 dimensions. And so the units in 2 dimensions is going to depend on, does this vector represent an acceleration or a velocity or whatever. Okay. And then the third one, so this was the sort of funny tilted one. The x-axis is that way. The y-axis is that way. We know that this angle is 20 degrees because that's how the coordinate system's given. And we know that the vector is also 20 degrees from the vertical, which means this angle is 20 degrees. So what's theta for this coordinate system? So you start at the x-axis, 90, 180. Okay. It's just 180. It's exactly perpendicular. No, it's not. It's exactly opposite the x-axis.
So from like 20, you had to add additional 160. I was a little confused.
Okay, so this red line doesn't matter except to orient ourselves to the physical thing, okay, to orient ourselves to the vector. But that red line isn't really a thing. So you go from the positive x-axis counterclockwise until you hit the vector. It's 90 to get there, another 90 to get there, and so 180. And so
the 20 degrees rather than the other one.
Because this one's skewed.
So that whenever you have a skewed, disregard.
Well, I wouldn't say it like that. I mean, that the 20 degrees in that picture is there to make so that we know how the coordinate system is oriented compared to the physical world and how the vector is oriented compared to the physical world. And once we figure out both of those two relationships, we just see that that vector happens exactly along the negative x-axis. If I would have made this angle 10 degrees, then it would have been more of a hassle to figure it out. We would have had to do a little more thinking about it. But I happen to just make the x-axis in the opposite direction of the vector. Okay, so u is equal to 10 times the cosine of 180, 10 times the sine of 180, and that's negative 10, 0. So what that says is, remember what these components are about. is if you start at the origin, how do you get to the head of the vector by first going parallel to the x-axis and then parallel to the y-axis? If this is your coordinate system, you go a distance of 10 along the negative x-axis, and then you're there. You don't have to go anywhere. You're already at the head. So there's no trip parallel to the y-axis that you have to take. Any questions about that? There's another way to represent this that comes up. So another common vector notation used more often in physics, but in some engineering too. You represent this vector as the x component times an I with a little hat over it. That's saying that the x component is the distance you travel in the direction of the positive x-axis. That's what that I means. And then after you've done that, you add that to another vector, the number that's the y component times this vector j, and with a hat over it, and that means in the direction of the y-axis. So from, let's say, part A above, we wrote our u as, what do we get for A? 3.42, negative 9.40. And that means the same thing as 3.42i minus 9.40j. I'm going to skip B and just go to C. So from part C, we got that that vector was equal to negative 10, 0. And that means the same thing as negative 10, I, 0j. So I just can leave that off. Don't add anything to it. Any questions about that? Once you have the components of vectors, so once you have vectors expressed as components, you can do mathematical operations and so I'm going to show you how to add two vectors. How to multiply a vector by a scalar. So these are the two things that we did graphically, but now we're going to do them using the components, and this is the way that's more useful for doing calculations. We can figure out the magnitude of the vector So calculate the vector magnitude. And then the last thing is we can do calculus with the vector components. So we can integrate vectors, differentiate vectors. Okay, so first, adding two vectors. So if you have a vector with components A, B, and you're adding it to a vector with components C, D, the resultant vector just has A plus C, add the two X components, and that's the new resultant X component. And the Y component of the resultant is B plus D. So keep components in their own, stay in your own lane row, and it'll give you the X and Y components of the resultant vector. And it's interesting that, I think it probably doesn't occur to anybody right at the first instant, but this way of adding vector components is exactly equivalent to that graphical method of adding vectors that we talked about, where you use the vectors as you start at a starting point, take one vector as a path to a new point, take the other vector from there to a final point, and then the resultant vector is the shortcut. So what we did in lab, this does the exact same thing. So if you do it carefully with like a straight edge and a protractor and stuff, and add these vectors and figure out what the new vector is and measure that and measure the angle, its components are this. If you're looking for something to sort of think through as you're trying to wrap your head around vectors, try to make sense out of that to yourself. Draw a couple pictures and see if you can figure out why that makes sense. And then the second one, multiplying a vector by a scalar. So let's say that we're multiplying the vector AB times the scalar C. So C is just a number. And this is equal to CA for the X component and CB for the Y component. So just multiply that number by both of the two components. And again, it might not be like obvious right at first. This is totally equivalent to the graphical method that we, the graphical definition of multiplying a vector by a scalar. When we look at this definition, does the order of these two vectors matter? What if we had added CD plus AB? Would that change the answer? No, because for each component, it's just regular addition, and we know order doesn't matter for addition. So the order of vector addition doesn't matter. The order doesn't matter here either. You can think of a vector being multiplied by a C on the right or on the left. It's the same thing. The order doesn't matter in this either. Okay, next, calculate the magnitude of a vector. So if you have a vector, so if this vector u is equal to AB, then the magnitude of that vector is going to be called, you write it as like the absolute value of a vector. And by the way, that makes sense with the definition of absolute value, because if we think of numbers that have signs associated with them as a magnitude and then a direction, either in the positive or negative direction, the absolute value just strips the directional information out of the number. Okay? And that's what we're doing here with a vector. We're keeping the length information, the magnitude, and throwing away any directional information. Okay? This is the vector without directional information. Can anyone think of what that calculation would be? That's right. Exactly. Yep. So if you think of that vector, have you guys all done this stuff before? Some of you, a little bit. Okay. Well, if you think of the vector as, if you think of the vector and the two components making up a right triangle, and it's just the Pythagorean theorem that gives you the length of the hypotenuse. And so this magnitude is equal to a squared plus b squared square root. That's just from the Pythagorean theorem. Okay, and now the last one, number 4. Doing calculus with vectors. You might think that this would be hard, but all you do is do the calculus individually on the different components, and the two components don't affect each other. So just do the calculus operations on the individual components separately. Okay, so for example, let's say we have a vector u. Okay, so it's a vector, so it has the vector symbol over the top, and it's a function of time. So that's how you write a vector, as a function of time. And this function is equal to 5t for the x component, negative 2t squared for the y component. And we want to know, so calculate u dot as a function of time. And we want to calculate the integral of u dt. So to take the derivative, we just take the derivatives of the individual components. So derivative of 5t with respect to t is just 5. Derivative of negative 2t squared with respect to t is negative 4t. And the integral so first, the integral of 5t with respect to t is 5t squared over 2 plus some constant, I'll call it c1. So that's the x component of the integral. And the y component is negative 2t, wait, yes, this is the one that's wrong. So I'm not integrating u dot, I'm integrating u. So negative 2t cubed over 3 plus c2. And that's the vector. And using that other notation that I mentioned, you could write part A as 5i minus 4tj. And the integral you could write as the quantity 5t squared over 2 plus c1 times I plus the quantity 2t cubed over 3 plus c2 times j. Those are just different ways of writing the same thing. And so I gave this final answer with those two constants built in there. But just like we did when we were doing 1D kinematics, and you had to integrate the velocity to get the position vector, we needed a boundary condition. We needed to know something about the position at a specific time. You'd have to know something about this function at a specific time for each of these two components to get those constants to go away. Yep. Yeah, whatever. Yeah. Any questions about that? Okay, so that's general vectors. So now we're going to represent kinematic quantities as vectors, the same way we represented them as numbers, kinematics along a line. So now we're going on to kinematic quantities, as vectors. So when we did motion along a line, the directional quantities, the quantities that had direction associated with them, time doesn't, but position does, displacement, velocity, and acceleration all do. And so now all of those things have to be vectors. So all the directional quantities that we're used to from 1D kinematics are vectors in 2 dimensions. So we'll have a position vector, a displacement vector, a velocity vector, and an acceleration vector. Time is still just going to be a positive number. Okay, so let me define position. That won't take long, and then we'll start with velocity next time. So the position vector. If you're tracking an object, okay, so like this baseball, and you have a coordinate system like this, the position vector is the vector that goes from the origin of the coordinate system to the center of mass of the object. So that red is the position vector. In 1D, what did we need to define before we could numerically represent the location of an object, before there was such a thing as position? Yeah, yep, zero position and positive direction. In 2D and in 3D also, what was our zero position before is now our coordinate system origin. And in place of the positive direction is the coordinate system axis orientations, coordinate system orientation. Okay, and once we define those two things, which I already did in this picture, now we can come up with components for that position vector in that coordinate system. Another way to think about it, it's the same thing. So another way to think of the position vector is just the coordinates of the object wherever it is in that coordinate system. And that's because of that, the fact that vector components are equivalent to the coordinates of the head of the vector. So that's the same thing. What are the units for the position vector? Still meters, yep, still length. For everything. Okay, anybody have any questions? All right, see you in lab tomorrow. I don't remember. I need to look at it.